Hello there, we're going to look at Static Engineering Systems B Part 1 today, which is basically your moments questions and then your resolving vectors questions. So here's this part of the specification that refers to it. Looks like a lot. These little symbols here, that means sum of. So you know the total of that's the horizontal forces equals 0, the total of the vertical forces equals 0, and the total of the moments equals 0, so the sum of there. And then we'll be using this quite a lot. Fx equals Fs cos theta and Fy equals F sine theta, and then understanding how to apply the law of moments. Okay, so if we look at the first question here, oh sorry, this is the part of the datasheet that's relevant. I mean, really, it's the same as we were using for Part C, which is Dynamic Engineering Systems, one of the 3 parts for Part C. But really, it's only here, components of forces, that we use when resolving vectors. You don't get given the moments equation. And this is what we need to remember for moments. So a moment is force times distance, actually perpendicular distance from the pivot. But that's never too relevant for us on in these questions. And then the law of moments is that, look, if something's balanced, if it's in equilibrium, then the clockwise moments equal the anti-clockwise moments. Now that only covers the turning effects. If something is in equilibrium, also you need the vertical forces to equal 0 and the horizontal forces to be balanced or equal 0. But that's what was mentioned here. Okay, so that's what you might have to state in a written question. Right, here's the first question. This is a moments question. You have a plank on one pivot, so there's just a single pivot there, and there's a force acting down on the right, and then there's 2 forces acting down on the left. So, of course, there is there's 3 downward forces, and there's no upward forces labelled. So you should notice that there will be an upward force at the pivot, which they never label. But we are not really concerned about at the moment, because we just need to figure out F. So we would apply this. It's in equilibrium, it is balanced, as the all will be. So the total of the anti-clockwise moments equals the total of the clockwise moments, and a moment is force times distance. This force would take it round that way. Around this pivot, if you step there, it's going to move clockwise. And these 2 forces would take it anti-clockwise. So all you need to do is figure out what the moments are. This moment is force 12 times 5, distance from the pivot. We are using this as our pivot. 12 times 5 is 60. What about this one here? That's a force. We need to work out its moment. Force times distance. 20 times 2, it's 40. So on the left hand side, or all your anti-clockwise moments, they would total up to 100 Newton meters. So that means on the right hand side we should have a moment of 100 Newton meters. Common mistake would be to say that's 100. No, we've worked out the moments, not the forces. The forces we had. So we know that the total moments on the left, or anti-clockwise, is 100 Newton meters. So the total moments on the right need to be 100 Newton meters. But moments is force times distance, which is force here, F, times distance 4. Okay, so we know that's 100 because we've added 40 to 60 on the left hand side. Simple rearrangement, divide both sides by 4, tells me that the force is 25 newtons. 5 marks for that. That was in the 2019 paper. That's what we were using. Alright, and the next is an example of vectors. So it's only moments and vectors here, so looks challenging, and I suppose there's a lot of information on that question, but you just have to approach it horizontally and vertically. Make sure you keep horizontal components separate to vertical components. Now I'll go back to here. Actually, this is what we're using, this little bit here. Think of a graph. You've got the x-axis, which runs horizontally along the bottom, and then you've got the y-axis, which runs vertically. So if you want the horizontal component of the force, you're always going to use cos. Force, cos, angle. And if you want the the vertical component of the force, then you're always going to use sine. So it's cos for horizontal, sine for vertical. Okay, so let's see this. So we want to know E. E is the equilibrant. That's the balancing force. So without E they would be unbalanced, but with E they are balanced. So let's look. I mean, this only asks for horizontal, but we'll solve it all. So horizontal, it says it's F cos theta. So let's look at this one, 26 newtons. It will have a horizontal and a vertical component. So this one, 26 newtons, I just do F cos theta. Force cos 20. That gives me 24.43. Make a note of which way that is. That is a force right and up, isn't it? So if we want the horizontal, that's to the right. Let's do this one, the 8 newtons now. Force cos theta. 8 cos 70 gives me 2.74, also to the right. Let's solve this one horizontally. 32 cos 60. So that's 16 newtons. And that's to the left. So you've got to take one way away from the other. So 24.43 added to 2.74, that gives you the total to the right. Take away 16 to the left, which leaves you with 11.17 newtons to the right, and that's your answer to this question. If they wanted to know what the equilibrant was as a total, then you'd have to go and do the vertical components as well, but you'd just do F sine theta this time. So just do sine of all of these. So 26 sine 20, 8 sine 70, and 32 sine 60. But make a note of whether they're up or down. And then if you add the two downs and take away the up, you'll get 20.68 newtons down. So that is, if E didn't exist, the resultant force would be 11.17 to the right and 20.68 newtons down. So my equilibrant, the thing that's needed to balance it out, just has to be the opposite to that. That's 11.17 newtons left and 20.68 up. Now if you wanted the equilibrant, what the actual equilibrant was, you'd need to just draw a triangle with 11.17 to the left and 20.68 up. And then you could use Pythagoras to work out the value of that extra side there. And then trigonometry if you needed the angle. Yeah, I mean, there's a lot to it if you had to work out E, but keep an eye out. A horizontal is written in bold there, so it'd be a shame if you solved the whole thing and wasted a lot of time there. So make sure you know what you've been asked for. Okay, so it's just this little bit here to remind you. As long as you know that X is used for horizontal and Y is used for vertical. There's your mark scheme. Next one, state one of the conditions that must be met for a body to be in static equilibrium. Well, I go back to specification, and it's this, conditions for static equilibrium. That's what you're putting into words. So the sum of the horizontal forces must equal 0. The sum of the vertical forces must equal 0, or the sum of the moments must equal 0. Another way to write that would be the sum of the clockwise moments equals the sum of the anti-clockwise moments. Okay, so there we go. Yeah, and that's kind of the third one is written at the top there. And there's your mark scheme. There's all your options there, just for one mark. Do not accept equal forces here. You can't say the forces have to be equal. That wouldn't work. You could say the horizontal forces have to be equal, or have to add up to 0, and same for vertical. But you must separate horizontal and vertical. Right, a moments question. So same approach as before, but there's a couple of other things to this. You see, this has 2 pivots. That's technically a little bit more challenging, maybe. This is a roller joint. This is a pin joint. This will give you horizontal and vertical forces. This will just give you vertical forces. Okay, so we have to kind of set this up. We've got 50 newtons down, we know, but that's not the only force. This one will be pushing up, that one will be pushing up, and we have a UDL. When you see these bumps, that's indicating a uniformly distributed load. It's 20 newtons for every meter, and we've got this bumpy bit covers 5 meters. Okay, so we know there's a force there, I'd add that on. We know there's a force there, I'd add that on. We've got the force there, and the UDL must be accounted for. It always appears in the middle of the bumpy section, and because it's 20 newtons for every metre and it covers 5 metres, that's got to be 100 newtons. We'll call that A, call that B, and you've set it up. If you were to set it up without all the pictures, it would look something like that. I've just transferred it over, so we've got all the forces on it now, and it looks a bit more straightforward. So I mean, yeah, the up forces must equal the down forces, so A plus B must equal 150 newtons. So if you work out A or B, you can work out the other one very easily. So A is a pivot or B is a pivot. Let's take A as the pivot, so we can ignore A for now because it's on the pivot. So that will have a clockwise moment, this one will have a clockwise moment, and that one would have an anti-clockwise moment. Okay, force times distance. So this one, 50 is the force, distance is 2. Let's do force times distance for this one, and that gives me the moment of that one. So the total clockwise moments is 350 Newton meters. So that one's got to be 350 Newton meters. But its moment is force times distance. Force, call it B, times distance 5. So B times 5 is 350 Newton meters. Divide both sides by 5. Tells you that B is 70 newtons. So we've got 70 up and 150 down, then you've got to have 80 up as well to balance it. So you can very quickly solve A once you've got B. So it's just a case of remembering the difference between a force and a moment. You can't just add forces and move them across. You must work out the moment of every force. So the clockwise moments equal the anti-clockwise moments. The clockwise forces do not equal the anti-clockwise forces. So we have to work in moments to solve this. There we go, that's all you need to remember. Mark scheme. Right, so we're getting to the earlier papers now, which are noticeably more challenging, I suppose, but it says calculate the magnitude and direction of force F. Now, there's only 3 forces on this, and you know, you could, in lessons, I'd be advising you to draw a dot, draw 200 up, draw your 200 coming down left, and draw your F coming down right. But, just like before, we should approach this horizontally and vertically. So, horizontally, the 200 has nothing, it's all vertical. So the horizontal of this is 200 cos 66. So 200 cos 66 will equal the horizontal of that. So you now the horizontal of F. Okay, this is what we're using. So you've got the horizontal of F, that one. Let's do it vertically now. Vertically, why? F sine theta. So it's 200 up, but you've got this down one, which should be 200 sine 66. So the 200 up needs to equal the down component of that added to the down component of that. So that might show you might be able to see that if you subtract whatever this component is, the vertical component of that, from the 200, you'll be left with the vertical component of that, which gives you this arrow here. So once you've got them 2 arrows, put them into a triangle. There's your real force. So you can use Pythagoras to work out the magnitude. With direction, you have the if you put the angle in there, you have the opposite and the adjacent, so you could use tan to solve that one. Mark scheme there for you to follow. Another moments one now, and more challenging, yeah, because it's not more difficult if you avoid the trap, but it does look more difficult because you've got something that's acting beyond the pivot. But look, it doesn't affect it. It just take your pivot at A. You've got a UDL. It doesn't cover the whole plank. The UDL only covers the meter. So you would put that UDL acting from the 0.5 meter spot there. It's 40 newtons per meter. It's only 1 meter, so it's 40 newtons acting down there. Okay, so you've got 40 newtons acting down. That moment from A would be 40 times 0.5. The moment from B would be, to give you, it's 26, so it's 26 times 1, and the moment from C would be L times 1.25. That one is clockwise, this one is clockwise, that one's anti-clockwise. So the equation would be 26 times 1, that's your anti-clockwise, equals 0.5 times 40 added to L times 1.25. And that's it, that gets you L. Once you've got that, L's down and this 40's down, 26 is up, so whatever's left over is A. So A plus B needs to equal L plus the UDL. Mark scheme there. Okay, this is similar, isn't it, because something goes past the pivot. You've got three separate forces. You've got the up force at A, you've got the up force at D, and then you've got to add the UDL. So this is going to end up with 6 forces. And for only 4 marks, you can tell it's one of the earlier questions. So let's deal with the, my first thing I would do is put a big arrow up at A and a big arrow up at D. Let's call it A and D. Your UDL is going to be, what's that, 2, 4, 6, 7 meters across. That's 35 newtons per meter. So that's, what are we looking at, 70, 140, 210, 245 newtons. 245 newtons acting from the middle. So the middle is 3.5 meters across. So that's the UDL. And look, you get credit for adding these on. So you've added the UDL, and then just figure out that's clockwise, 45 times 2. Take A as your pivot. This is clockwise, 70 times 4. A lot of people will put 2 there. You've got to make sure that's the distance from the pivot that you're dealing with. The UDL, oh sorry, I'll do the last clockwise. It's 20 times 7. So add those 3 moments up, and that's your clockwise. I missed out 70 times 4, did I? No, 45 times 2, added to 70 times 4, added to 245 times 3.5, added to 20 times 7. So that's your clockwise. And that's got to equal your anti-clockwise. Well, if we put the pivot at A, the only anti-clockwise one is at D. So that's got to equal D times 6. 6 meters from the pivot. Really challenging one, that, because there's so many forces, so you've really got to keep it organised. But the approach that I'm encouraging you to do is, when you see it, the first thing you should do is put an upward force on the pivot, and then sort out your UDL. Put that on. Then you'd probably write down clockwise moments equal anti-clockwise moments, and then just do your best to set up the equations. It is tricky to follow these mark schemes because there's a lot to it. But you can see there's one moment, there's another force times distance, there's the force, well, it's 35 times 7, that's working out the UDL, and that's putting it halfway across, and there's the fourth. So there's all your clockwise ones, and they must equal all your anti-clockwise ones. Alright, here's a vectors question again. This asks for the magnitude and direction line of action. We'll ignore the line of action for now, but of the resultant force. So just deal with it horizontally and vertically, just like before. So you have, there is a resultant force, so they're not balanced. So you have 3 cos 30. So we'll be working horizontally. 3 cos 30 added to 4. These are kilonewtons, so 4,000 newtons. There's no cos or sine there because it is just purely horizontal. And then there your ones to the right. The ones to the left will be 5 cos 45 and 2 cos 65. Remembering that we're working in kilonewtons there. Okay, so take the left ones from the right ones, and you've got your resultant horizontal. Sorry. To do vertical, what is it? 3 sine 30. 4 doesn't have any vertical. And 5 sine 45. There you're up, and your down is 2 sine 65. Take your down from your up, and you've got your final vertical. So you've got your vertical, which would be up. You've got your horizontal, which is, I'm guessing, is to the right, and then you just need to figure out what the resultant force of that is. Here's your mark scheme, but again, yeah, tricky to follow. They deal with horizontal and vertical of each force before they move on to the next force. Okay, that's it. Now, listen, we've spent hours in lessons on these, so I'm not thinking that a little 20-minute video is going to solve all your problems. But just to summarise, I've shown you what you need to remember. That's in red. But just be aware of that little equation in the datasheet. I'll go to the very start actually. Just be aware of this little bit here that tells you the ones you can use, and then when you get something that's any force that's at an angle, you're probably going to want to get its horizontal and vertical components. And if you can keep it organized, make sure the examiner can follow your work. You have a horizontal section, and then put it in a little box, and then you have a vertical section, because you need to be able to follow your own work as well. Okay, I hope that was of some use. Thanks for listening.